Hi guys. Thanks everyone for coming. I'm Andrew Stapleton. I'm a firmware engineer at Pebble. I've been with Pebble for about a year. And I'm going to talk to you about the voice system on Pebble. I'm going to start with a basic intro and an overview of how the system works. And then I'm going to go and start looking at the dictation API that we've exposed to you. I'm going to go through an example app as well, and then I'm going to explain how the actual system works. I'm going to finish up with some do's and don'ts about how to use the API, and then talk a little bit about the tools that we've created to make it a little bit easier to develop for voice. So, as an intro, really excited to give you guys the first freeform input for Pebble. Up till now, you've only had buttons or whatever you could get off the phone or the web. And for the first time, we can give you direct text input from voice in the form of the dictation API. And I think we're all pretty excited to see what you guys can come up with. And I believe there were some good examples last night at the meetup, which unfortunately I missed because I was finishing my presentation. So this is a very high-level overview of how the system works. We get our audio in from the microphone. The microphone is located just behind the little hole in the watch that you can see in that image. And yeah, it's a hole, but it's still waterproof, so you can still get it wet. We actually have a little swimming robot in the factory, which makes sure that we aren't getting water into our microphone hole. Then we pipe the data into the microcontroller. We process that, and I'm going to go through what we do in a little bit more detail later. We offload that to the phone, and the phone sends that off to our cloud recognizer. And the cloud recognizer then transcribes the text, transcribes the speech into text, gives the text back to the phone, which forwards it back to our watch, and we show it on the UI. So, a few examples about what you can do with the API. I think a few of you guys have thought of some cool things already. But things off the top of my head, general text input, just like you want to name something in your app, or like you want to take a note. I know an intern of ours created a voice commands app a while ago using our prototype APIs, and he could just play some music on his phone, or he could get the weather and show it as a notification on the watch, and that was really cool. Translation tool could be pretty useful. Search or contextual query interface, and that's what I'm thinking there is something like Siri or Google Now. There's a service called Houndify, which which you can use as well, which is pretty cool concept. I actually wanted to demo that for this demo, but I didn't quite get it ready in time. Some sort of messaging, and I believe there's a Twitter interface that's one of you guys came up with recently. And I know Neil, one of our guys, actually has a little tweet app which lets him send something off to the web. So, the basics of the API. We try to keep the API simple. It's quite complex under the hood, but we wanted to provide an easy way for developers to get the freeform text input. So it's the three most important functions are creating a session. You need to provide a buffer size, which is how much memory we will allocate for the text that we receive from the phone. There's a callback you need to provide that gets the status of the transaction and also your transcription, and you can provide context as well. The callback, as I mentioned, I'll go over this a little bit later, and start. Those are basically the only three things you need to define or use or define to use the API. When you call dictation session start, it's going to spawn the same UI that you may have seen on the voice reply if you have an Android. And this is what it looks like. The user can speak, and when the user has finished speaking, either we detect the end of speech or the user can press the middle button, and then we show the transcription on a transcription window. And broken down, we see, yeah, spawn the UI. You might see a loading bar. We have to ping the phone, and the phone sets up a session with Nuance, so there's a little bit of delay there. Then the user starts speaking. Number 2, at the end of speech, you might see another loading bar. That is us getting the data from the cloud recognizer. And then we show the transcription window at the end. If the user accepts the transcription, we exit the UI and we return the text to you. If the user rejects the transcription by pressing the back button, it goes back to the start of the UI. Hitting the back button again will exit the UI. There are also a few error dialogues that we're going to show. Number 2 over there happens if there's an error while the cloud recognizes transcribing the text. Either it doesn't recognize the speech, or there's a lot of background noise, or an error just happened during that process. Number 3, a little bit vague, but there are a number of other errors that can happen during the process, and you'll get that error dialogue. These dialogues are typically shown 3 times, and then if it happens a 4th time, either one of those errors, we show the dictation not available, and we exit the UI and we return a status code in the callback. These are a few more severe error dialogues. Number 1, the Bluetooth connection. That happens generally when you spawn the UI and you don't have a Bluetooth connection. And it'll stay up until the user connects their phone, or the user just backs out of that dialogue and you exit the UI and you get an error code again. No internet connection, similar story. The phone hasn't established an internet connection, so we can't give you a transcription. The 3rd one, we need to have usage logs enabled on the phone, and if the user has disabled that, we're going to show that dialog, and again we're going to exit the UI and we're going to return that disabled error code. There are a few things that you can use to improve the flow or to handle the error dialogues yourself. The first one is this allows you to disable the error dialogues by setting that bool to false. That means that you're not going to see any of those error dialogues. We're just going to bomb out of the UI straight away, and we let the developer handle those error codes. And you should try and give your user some useful feedback about what happened. The second one is being able to disable that confirmation dialog at the end. So if you don't want to interrupt the flow with the user having to hit the select button to accept the transcription, you can disable that. And that's pretty useful in examples where it's a bit jarring in the flow. For something like the Twitter example, you probably want to be able to confirm that before you send your thoughts up into the cloud, especially if they weren't quite well recognized enough. But like a translation app, it might be a much nicer flow just to disable that. You can also stop the session mid-flight. That exits the UI as well, and you won't get an error code. You just carry on as normal. This shows what the UI looks like without the confirmation dialog. There's no backing out. It just goes from the beginning to end. If there's errors enabled, you'll still see the errors and it will go back to the start. Otherwise, it exits the UI once you've got a transcription or an error. Oh, sorry, errors, you will see the error. Right, so the demo I made for you guys, I was going to live demo it, but we don't quite have the camera set up how I was expecting it to, so don't have that, but I will give you some videos to show what I've done. And the code is up on GitHub. So it's a very simple translation tool. I'm using a dictation session to get some text. I'm sending that up to the Google Translate API, and then going to show that text to the user. Please excuse the UI. I am a very reluctant UI designer, and with limited time, I've decided to focus on it actually working. So, going to go through a little bit of my code just to get this working. You'll see I defined a buffer size. 512 is a big enough number that you're not likely to ever, or not likely to, for the user's not likely to say enough to fill that buffer. But it's also not too huge that you're going to be taking too much of your RAM. You can play around with that number, experiment with the kind of input that you're expecting, and it doesn't have to be so large, it can be a lot smaller. Bear in mind, though, that if you're expecting different languages with some code points that are not standard ASCII, those are going to be much larger, like 3 to 4 characters per actual character. So you've got to take that sort of thing into account. When you create the session, you provide that callback. You also need to check that the session is valid, and there are a few reasons why that can fail. The first is that you use it on the original Pebble, which doesn't have a microphone, or there's actually no Bluetooth connection when you try to create the session. Or the phone app is actually an old version and doesn't support the voice APIs yet. Other two important things: I'm starting the session from a select click handler, and then I'm handling the session result. And see, I checked the session status is successful, and then I use the text that I receive. For my first short example, I'm not actually doing it for that text. I'm just going to show the basic flow in an app. So I've got this video, user speaks, hits select or stop speaking, and that's our text. And then that's the first part of my app. I'm saying the English version is good morning, everyone. So the next thing I did was I added some app message code. I'm not going to show the app message because we've all used that before. But that sends that to the phone where I've got some JavaScript running that sends that makes a request to the Google RESTful API and gets a response, and then I show that response. And I'm translating this to German in the first example. And that isn't very readable. It says Guten, you can pronounce it.
Guten Morgen allerseits.
Thank you. Okay, so now I'm going to simplify this because the tick mark is not very useful. We'll select on the confirmation dialog. And I also thought that I could make this app a little bit more useful to myself. Francois, my colleague, always struggles with my accent, so I thought that if I converted what I'm saying to French, we might be able to communicate better. So that's this. What would I like to say to Francois? And I've been trying to get this through to him for a few weeks, but he just doesn't seem to understand. It says, you still owe me money. And that's, vous me devez encore de l'argent. Okay, and I can actually show you that on my watch afterwards if you like, if you don't believe that I did it. Okay, so how it works. The first part is we have a microphone, and we need to get the data from the microphone to the microcontroller, and we need to convert the data that we get from the microcontroller to something useful. And the reason for that is that we use what's called a MEMS microphone. The MEMS stands for micro electromechanical systems, and it's basically a very small mechanical element on a chip. Other examples of that are accelerometers, gyros, magnetometers, all very fancy tech, very cool. And that gives us an output of what's called pulse density modulation, or PDM, at 1 megahertz. The signal that we see looks like that bottom signal. The blue bits are ones, the white bits are zeros, and that represents a sine wave, as you can see, superimposed on top of that. It's very noisy data, but we oversample it so that we can low-pass filter and combine samples to give us a much better signal afterwards. We pass that 1-bit signal into what's called a decimation filter and a low-pass filter. The decimation is a process of undersampling. So we go from 1 megahertz to 16 kilohertz through the process of decimation, and the low-pass filter gets rid of the noise. So we end up with a signal down at the bottom, which is much nicer. And that's 16-bit, and it's called PCM, pulse code modulation, and it's just, you know what 16-bit is. Like, you got a, for each value, each moment in time, you've got a sound value corresponding to, or an integer value corresponding to the sound. Right, so we've got the 16-bit, 16 kilohertz signal, And now we need to get it off the watch because we can't do the speech recognition on the watch. So we use a speaks encoder. We chose Speaks because it was developed specifically for VoIP applications, and it performs very well. It outperforms a lot of telephony codecs in compression ratio versus quality metrics. It's also very tunable, so we can tune it so that we can actually run it on our processor, but still get a decent enough quality that we can recognize the speech afterwards. It recovers from drop frames, which is very useful when you have a Bluetooth connection, which can occasionally drop frames. And it also has a few additional bells and whistles, like noise cancellation, echo cancellation, and the thing that we use to detect the end of speech is voice activity detection. Right. Under the hood, it's doing what's called code-excited linear prediction coding. I don't know the details. It's all very complicated. We just use a library. It was optimized for our processor because even as good a performer it is, it's still very demanding on our hardware. That converts PCM, which is the 16-bit, 16 kilohertz signal, to a sequence of frames, which equates to a 12.8 kilobits per second data rate, and that's down from 256 kilobits per second. Of course, as I mentioned already, it comes at a cost. We're doing quite a bit of work on the CPU when that's going on, and I'll come back to why that's important a bit later. Right, the last part is that we forward the data to the phone then packages it up, makes a connection to our cloud recognizer. And our cloud recognizer that we use is Nuance. They've been around for a while. If you've used the Dragon virtual assistant or Siri, they were behind those technologies. The recognizer then returns us text, and we show it to the UI. Pretty simple. Right, so a few do's and don'ts. You only ever need to create one session instance. It can be reused as many times as you like, but creating more than one is just a waste of RAM because it's quite big in size. There's a lot that we need to do under the hood.
Sorry, when you create a session instance, you've got to have 1.5K free in your app space to be able to.
Yes. Otherwise it will turn null. As I said before, we're doing a lot of work on the CPU when we're encoding, so try not to do any heavy processing. Animations is a good example. It's probably not a good idea to be doing animations at that point anyway, because your window is going to be obscured by the dictation UI anyway. Try not to do any app message communication. That's going to compete with the Bluetooth packets we're sending our data in. Then we've already touched on the 1.5 kilobytes. Clean up your session afterwards to free up that RAM. And I mentioned this before. If you decide to disable error messages, it's a good idea to give your users some useful feedback as to why things failed or what they need to do next. I'm sure you'll experience it anyway. Some common failures. What I found is that most failures are due to the user not speaking clearly enough, or they speak too quickly. If anyone's used Siri or Google Now, you'll know that you have to kind of slow down your speech and enunciate it a little bit better. It's the same story here. Background noise is another thing. It's pretty tolerant of some background noise. Like when you guys were talking at the beginning of this, I was actually testing a few transcriptions and it was working fine. If you're outside in a much noisier environment, then we can't actually detect the speech from the noise. Encourage users to keep phrases brief. The longer your transcription goes on, the more error there is likely to be. Another thing to keep in mind is the voice language setting on the phone might be different to the watch language setting. Currently, we don't actually expose. We don't have any feedback as to what language is being said on the phone from the watch, but we're going to expose that in an API shortly. Right. Development tools. Dictation API works on a local emulator, and you can stimulate it from the command line. This video is a lot less clear than I thought it'd be, but it's basically this text underneath. You say Pebble transcribe, you give it a transcription. 0 is the status code. There are a few other error codes you can use, and that will appear in your UI in the transcription window. Right, and you can use the app like you would on the watch. That's going to be in Cloud Pebble as well soon. Right, all the documentation is up on the preview site, previous version of the site, a Pebble SDK site. There's a guide written by Chris Lewis as well up, and this example app is up at that address. You'll need to get an API key from Google, and I'll put that in the README. It's not there yet. So to recap, we had a look at the new dictation API. I gave you an example app, which shows you how you can use it. I went through the internals of the voice system and went through a few do's and don'ts, and yeah, that's it. Are there any questions? So I'm just going to repeat the question for the recording. The question was whether we can set the voice language via the API. Something we haven't thought about. Definitely take it as a suggestion for when we implement that. Yep.
Would the language be passed back to the status callback, or would it be available in advance?
Not yet. We're going to have to query it. Sorry, repeating the question. The question is, will the voice language be passed via the status callback? And we're going to expose it as a call on the session object. We don't expose it. We don't pass it back via the session, the status callback just yet.
Can that be available as soon as the session is created?
The question was whether it will be available when the session is created. Answer is yes.
Are you thinking about using any an offline recognizer? Because obviously you need to be to contact nuance. Whereas I think on Android phones there's kind of like local voice recognition.
The question was whether we're going to use local recognition on the phone.
Yeah.
We don't have any plans for that. We can maybe chat about something like that afterwards. The back.
Two questions. First, can this be triggered from a watch face?
First question is, can it be triggered from watch face? We do not prevent that, so yes.
Okay. Second, is there any way to cancel, or is there an automated timeout similar to how iOS has with their Siri?
Question is whether you can cancel, whether there's a timeout. I actually forgot to mention that. During the UI flow, when the user's speaking, there's a 15-second timeout, and that'll automatically send the result off to Nuance, and if there was speech, you'll return that speech, otherwise we'll back out of the UI. You can also pull the dictation session stop, and the user can back out with the back button. Does that answer the question?
I was wondering if there's a programmatic way.
Yes. The programmatic way is to call dictation session stop.
Okay, sorry.
No problem.
I was wondering what the reason was behind not enabling showing the UI if the phone app is not running. So if the phone app is not running, you're not getting a session back, and you can't show the UI. Why don't you allow us to always present the UI with an error message, so that we don't have to handle this case specifically?
The question was why we do not let you show the UI if the phone app is not running. There's no connection to the phone, so we don't create a session, and that's it's not particularly useful if you can't connect to the phone, I guess.
Well, an error message would be useful, like that's just a case that we have to handle.
Are you saying when you do dictation session start, it does show? It should show an error message.
I can't call that on null.
Yeah, but null is your error. You don't get a UI. Your UI doesn't spawn when you call dictation session create. Anyway, I'll speak to you afterwards, and we can talk about that. Yep.
Is there a way to sort of maybe bypass having the text come back and maybe just exposing to a companion app through Pebble somehow?
Question is whether we can deliver the text to a companion app instead of the dictation UI. Is that
Yes,
correct?
basically.
Not yet. It's a good suggestion. Love to talk to you about that afterwards as well.
Is there any chance of getting access to the raw microphone data at some stage, like with the accelerometer?
Yeah. The question was whether you can get raw access to the microphone data. Not at this point. We haven't decided whether that's going to be done yet. Put up on the suggestion wall though.
Well, one of the sensitivities about that is we don't have any per app user permissioning at the moment. So we don't want to enable any watch app, watch face to start recording audio straight from the microphone without the user being aware of what's happening.
Anything else? Cool. Thank you very much, guys. I'm really looking.